Once again, here are our two options. Please see the prior videos to explain at least option 1 in detail. In this video, we're going to tackle option 2, and we will calculate the radius of Earth using the angular resolution limit of the eye. Once again, these are our assumptions that we have explained within the series. Perspective changes with the observer, especially with regards to height change and their effect on transversal and orthogonal lines within 1-point perspective, objects getting smaller with distance within perspective, and the use of the convex lens system within our eye, small objects disappearing from vision, use of the angular resolution limit and diffraction, and the horizon rising to eye level. These are our parts of our series. We have covered angular resolution within the first 4 parts, and now we're to the world in which we were given, or at least is assumed. So within this part we will discuss Aries failure, axial tilt and the human eye vertical field of view as a means to derive Earth's radius, derivation of the Earth's radius by the extrapolation of the angular resolution limit of the human eye, derivation of the parabolic drop rate within perspective, as commonly known as 8 inches per mile squared. So first, a little bit about Aries failure. Because we've gone through refraction, this will make a little bit more sense, and it's a very interesting experiment used to detect the luminiferous ether, and this experiment is noted as Aries failure. I encourage you to read up on the luminiferous ether within the Wikipedia page, and you'll see kind of how things progressed from a faulty presupposition of Earth's movement. But Aries failure used an intersection between motion parallax and refraction. So if a stationary telescope points at a stationary star, the telescope will never require modification to observe that star. If either the star or the telescope are moving, an adjustment must be made throughout that movement to maintain the same observation. So it was noted in 1729 that a telescope had to be tilted 5 degrees to get a star in the center of the telescope. Since the Earth was assumed to move and the star was stationary, this was the presumed reason for the tilting of the telescope. So Airy decided to test this idea. The 2 presumed reasons for their observed phenomenon are below. So the first postulate was that you had a stationary star and a moving Earth, and then the second one was that you had a moving star and a stationary Earth. So stationary star, moving Earth, moving star, stationary Earth. So within the first example on the left, as the starlight is descending, we'll take it as these little balls of light, and the telescope is tilted and moving. As the starlight continues to descend, the Earth continues to move, and the tilt of the telescope allows that center yellow dot of light, we'll call it, it stays within the center frame. And so you can see the telescope maybe on the left. When the yellow dot hits it, it's at the very top of the telescope, but in the middle. As this telescope continues to move to the right, let's say to the very far right telescope, the dot stays essentially in the middle as it descends down the telescope. And so you see the same star within the telescope during that movement. In the second postulate, you have a moving star, and so it is the Earth is stationary, and the star is moving such that you tilt your telescope so that you can see the descending light continue down the telescope in a straight line. So in other words, as this star moves from left to right across the page, it's dropping these droplets of light, we'll say, and they are maintaining themselves as the star gets further and further to the right within the center of the telescope. So again, a stationary tilted telescope keeps the moving descending light in the center. So to test these options, they filled the telescope, the tilted telescope, with water. which would now refract the incoming light. If the light hit the water at an angle, it would bend, and as the telescope kept moving, the star would be lost from the center view. If the ether and the Earth moved independently, you would lose the object with greater tilt. So conversely, if the ether and Earth moved dependently in unison, greater tilt would allow you to see the object in its entirety again. So what he found was that the ether and the Earth moved independently from one another. As he tilted the telescope, he saw absolutely nothing. And he just essentially, the water had no effect, and the light still hit the observer. So it was deemed a failure to detect ether within the moving Earth as independent, or excuse me, as dependent and moving with the Earth. He never mentioned the more interesting aspect of this experiment, though, that the Earth was stationary and that the atmosphere and ether moved. Later experiments by Michelson-Morley, Michelson-Gale, Sagnac, and others in the late 1800s and early 1900s continued to prove that the Earth was stationary with various different experiments, but they maintained the assumption that the Earth moved, and they modified their findings to say that the ether must not exist. And this required light to become fixed and matter to expand and contract to meet it. And shortly afterward, relativity was born after a Lorentz contraction with an E equals mc squared equation that everyone is so fond of. These ideas then fed off one another with equations that stated something must exist, and therefore it did exist shortly thereafter, and we became lost in a theoretical, timeless, dimensionless multiverse. All of it based on the faulty assumption and presupposition that the Earth rotates. Before moving on, let's do our first calculation of Earth's radius using the optics of the human eye. For this one, we'll use the vertical field of view, which ranges from 130 to 135 degrees. It's slightly better below the eye because, or than above, because of the superior orbital rim, but the angle represents about 65 to 68 degrees above your eye line and 65 to 68 degrees below it. For a refresher on Polaris, let's return to our diagram and explain the distance relationship. Recall that Polaris, which is fixed in the sky, moves higher about 1 degree every 70 miles or so as we go north. They chose 69 miles. The alternative explanation is that if I move 70 miles closer to Polaris, it rises 1 degree within my perspective. But assuming that the Earth is curved and Polaris is fixed, if a person walks 23.4 degrees south to 90 degrees north, they would cover about 7,824.6 miles on a sphere. So if this represents 23.4 plus 90, or 113.4 degrees, then 0 to 90 degrees north would be about 6,210 miles, or 69 times 90. So you can see we've just taken this globe representation, they've tilted it to a fixed, unmoving Polaris, thinking themselves that they are moving across the Earth to keep the fixed object within view, going 1 degree every 69 miles. If we lift the arc off of the Earth, and we can kind of represent it here along a straight line, and we see that as we move south, we can, using a sextant and comparing the angle to the star with the horizon, we can get our latitude. We've already gone over that. But as we'll see, what's really happening is that instead of your vertical field of view being 65 to 68 degrees, they made it 66.6 degrees and failed to take into consideration an additional 23.4 degrees of vision that occurs within perspective. Intentional or not, without this additional distance, they had to tilt the Earth. So we'll explain that a little bit here. Looking at our corridor, our vertical field of view limit is here. Over on the left, you can see how the angles diverge and converge from the light source, and they are converging back on our lens. So think of this limit as a limit of lens convergence. So this This limits the angle at which we can create an image above us or below us, looking straight on at the horizon. So when we collapse our corridor around this angle into our perspective, it becomes the closest angle to our eye. In other words, it's the closest angle with which we can view those paint stripes, essentially. We can drop a vertical line from the points where these two angles reach the ceiling and the floor, and again, it limits the distance along the floor or ceiling that something can be viewed above or below us. But again, on a straight line view, we can still see an additional 23.4 degrees further. So again, our paint strips that are attached to the ceiling or floor may limit there, but looking straight on at an object, we still get an additional 23.4 degrees of vision. So if we're viewing a distant star, however, we're estimating its distance to our eye. So it's essentially our eye line if the object is setting far away, right? So it is taking into consideration that 23.4. So if I'm using a sextant to measure something and comparing the horizon and the object, I'm evaluating it according to these vertical angles until 65 to 68 degrees, which is a maximum. After this point, you must tilt your vision upward to view the object. But if I don't take into account the vertical field of view, I do not take this additional 23.4 into account. So I believe something is 90 degrees away when it's actually 90 plus 23.4 degrees away. If we use 66.6 as our vertical field of view above our eye line, an object along the ceiling would be a certain distance plus 23.4 degrees. Again, this represents the other angle of that right triangle. So this distance is what is ignored when viewing Polaris from 23.4 degrees south. So we'll assume the vertical field of view as 133.2, which is just 66.6 degrees split above your eye line, 66.6 below. We'll recall that when something is high up, we are essentially rotating these angles down within our perspective to our eye line as they approach theta and set into the lower eye line. Again, once theta is met, that sets the lower half of our visual field, and whatever is left above our eye line becomes the top 50%. So looking at our diagram, we can reverse it to fit within our corridor at the maximum height and distance at which it can be observed over here on the right. So we'll just flip our diagram, flip the star and the eye, and the height there represents the furthest distance and height it can be. So again, when rotated down, this is the furthest point along our horizon that we can see. As discussed, the line represents 90 degrees plus 23.4. So from the 0 point to 23.4 represents about 1,614 miles, 69 times 23.4. And from the 23.4 mark to our horizon line is the basically the 90 line to Polaris, or 90 times 69, which is 6,210 miles. And adding them up gets us our 7,824.6 miles. As you can see on the lower left, we've kind of outlined how those distance relationships work themselves out. The red line represents that vertical line dropped along from that 66.6 degree triangle along 23.4 degrees, dropping it down perpendicular to the eye line. So if I believe I'm on a globe and 7,824.6 miles represents an arc length from 23.4 degrees to 90 degrees, and 6,210 represents an arc from 0 to 90, then if I multiply my quarter arc of 0 to 90 by 4, I get a circle with a circumference of 24,840 miles and a radius of 3,953 miles. Keep in mind the radius of Earth is 24,900 miles and a radius of 3,963 miles. So again, what they think is happening is up here on the right. What is really happening is that they are not taking into consideration that additional 23.4 degrees that is dropped from the vertical field of view to our eye line. So this is one way they use the optics of your eye to tell you that you live on a sphere. Of note, the implication when viewed correctly within perspective is that when viewing celestial objects, if we move 70 or 69 miles closer to something, our horizon opens up about 1 degree, or it moves along 1 degree within perspective. Put another way, If we stay fixed, we see an atmosphere with a radius of roughly 7,800 miles and a diameter of 15,600 miles. And again, this assumes that we could actually see that far, which I don't believe to be the case. I believe we are seeing within a personal atmospheric lens to a much less of a distance. And for more information on that, just refer to part 1. So let's summarize where we've been up to this point. I want to impart to you that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction phenomenon. So option 1, again, the ground is brought to your eye level. The person disappears from perspective by walking straight away and vanishing bottom first from things getting smaller with distance and an angular resolution limit. And here's some of the examples that we've gone through to this point. We have our lid disappearing into the floor. We have some calculations that we can use to determine our horizon distance and or loss rate with height change. Let's now turn to our second option. So option 2 was we had the eye is brought to ground level. The vanishing person is represented orthographically without regard to perspective, and your focus continually shifts downward to observe them going over a curved surface and vanishing at the same rate. It just so happens as the angular resolution limit of the human eye, and we will show that momentarily. So again, within this diagram, our eye line shifts downward. It must shift downward to observe an object physically going over curvature. Perspective effects and angular resolution are ignored. And again, putting it together so you can see them side by side, the loss of information at our horizon, just to restate our argument, is either an optical phenomenon or a physical one. If it's physical, they disappear by walking over the horizon. And if it's optical, people disappear by angular resolution limit of the observer. So with these options in mind, we will now use the angular resolution limit of the human eye to calculate the radius of Earth. The first step in doing this is to assume a curve, and that the lower 50% of our vision represent a physical blockage of our vision. So we need to translate our linear perspective into an exponential one. So again, the angular resolution limit of the human eye is 1 arc minute, or 0.02 to 0.03 degrees. We have to get a more precise value though, or the range will be too high for the radius of Earth. So we need to plug in some good numbers for distance. Since we're seeing boats go over the horizon, we'll use a small pupil diameter because we're focusing at far distance. So again, the diameter of the pupil ranges from 2 to 4 millimeters in bright light and 4 to 8 millimeters in dark. Recall that refraction effects are highly varied, so we need a relatively non-refracted wavelength to get a more consistent value for a distant object. So orange-red wavelengths are less resolved than blue, but they are less subject to the highly variable refraction effects and atmospheric scatter that we witnessed before. Recall that refraction and diffraction are different. One is the change in angle through a new medium. One is the change in angle from passage through an aperture. So the wavelength of light ranges from 400 nanometers of the purple range to 700 nanometers of red. We want to use the more orange-red later wavelengths. Since we're looking at objects far away, we'll use an orange-red wavelength of 666 nanometers. The pupil narrows when it focuses on distant objects, like we said, so we'll use a pupil diameter of very low of 2.16 millimeters. So we can solve for theta using a predictable occult preoccupation with numerology and the number 9, such that theta in radians is equal to 1.22 wavelength divided by diameter, which is 666 nanometers divided by 2.16 millimeters. That gives us our number in radians, and which is also adding up to 9, as we'll go through and that gives us a angular resolution theta of 0.0216 degrees. So again, I chose these numbers on purpose. The numerologies of 6s and 9s as 666, which adds up to 9, and 216, which also adds up to 9, and 3762, which also adds up to 9, are on purpose, very intentional. The subject is vast, but it is their mark. Just like 24.3 degrees is 9, and 66.6 degrees is 9, 432 hertz is 9, the sacred geometry of sound and cymatics. The seconds, minutes, and hours all are increments of 3, 6, and 9. There are Fibonacci pairings, flowers, and trees of life, and numerous other examples of numerology that seem to stem from Pythagorean and Ptolemaic schools, alchemy, Hermeticism, and Babylonian, Egyptian, Greek paganism. In essence, the 6 is man's number, the 9 is their God number, and the 666 is how man becomes God, as 666 is equal to 18, which is equal to 9. I won't go into that too much at this point. Just know that the numbers that I chose were purposeful. So we theta as equal to 0.0216 degrees for long distance vision and a pupil diameter at the lower limit. So we can now use this angle to see how far the average 6-foot person can see, just like we did with our object examples before. So distance is equal to the height divided by tangent theta, which is now equal to 6 feet divided by tangent 0.0216, gives us 3 miles. With theta and our max horizon distance known at a 6-foot elevation, we can solve for the amount of information loss at that distance. So again, we flip the triangle back around, and this person at this height would lose 6 feet. So under optimal conditions with a minimum pupil diameter of 2.16 millimeters for long distance viewing and a wavelength of 666 nanometers, we can see that when looking 3 miles away at a 6-foot observer height, anything smaller than 6 feet below the horizon cannot be observed. We now have the 2 triangles with which we can construct a curve. We can fit the height and drop triangles together as we look down across the curve to view a distant object disappearing over it. So again, the first one is the distance that we calculated for a 6-foot person using theta at 0.0216 degrees. And the second one is the loss of information that that person would be granted across that 3-mile distance. And you can then use those triangles together to get your rate of curvature for a 6-foot person observing someone go over the curve. So as an aside, if we extend the lines, you can see that we underestimate the loss at this pupil diameter and wavelength nearby and overestimate the loss using curvature with greater distance. So again, if I assume a curve now that this green person essentially is walking over a curve, you see that the lines don't really match up between the triangle. The straight blue line and the brown line do not match up. The curvature rate is underestimating it nearby, and it is grossly overestimating it far away. So for example, at 100 miles, we expect to lose roughly 184 feet by angular resolution at 0.02 degrees, but with curvature at 100 miles, we're losing 6,660 feet. So the takeaway is that with distance, diffraction plays less of a role than refraction does. That's the takeaway here, because we do see the bottoms of things lost at a greater rate than simply 184 feet at 100 miles. By extension, the use of infrared camera technology is very useful over long distances since it is more prone to diffraction issues but experiences less refraction at the same time. So because refraction does play a decent sized role, that the infrared camera technology is proving to be a very good tool to view these distant objects, which again do not have anywhere near the expected rate of loss, such as 6,000 feet of loss at 100 miles. It just doesn't exist. So our rate of curvature is 6 feet lost at 3 miles from a 6-foot observer height. We need to approximate the angular resolution limit line within our curve as close as possible. We only have 2 crossover points, one at 0 miles and one at 3 miles. We know that the size change must be exponential within perspective in order to get a curve to develop out of it. Can't be linear. So we will solve for the Earth's radius by knowing the arc length and arc angle. You can see here we've just taken our 2 triangles, placed them against a curve for a person walking over at that rate of 6-foot loss over 3 miles, and we have then extrapolated it along a greater circle. So the observer would assume they are watching a person descend from their point of view across 2 theta at 3 miles. The first theta, 0.0216 degrees, would represent the observer height at 6 feet until reaching 0 feet, and the second theta for the drop from 0 feet to minus 6 feet. So we can therefore take our arc angle of 2 theta across an arc length of 3 miles, or we can take the drop rate of 12 feet across 3 miles. Either will give us r for the greater circle. We can now solve for the radius of Earth from the angular resolution limit of the eye as our segment here with r along the radius, or along the one aspect of the triangle, and 3 miles as our opposite end, and the angle being across 2 theta, which is 0.0432 degrees. That will give us one number, and the alternative is to use the ratio of 12 foot over 3 miles is equal to 3 miles over r. Both will give us the numbers listed below, so we get for one number 3,978 miles, and for the other one 3,959 miles, giving us an average of 3,969 miles. So for our circle based on the angular resolution limit of the human eye, we can calculate a radius of 3,969 miles, and the circumference then comes out to 24,938 miles. And coincidentally or not, the Earth's radius is said to be 3,963 miles with a circumference of 24,900 miles. We can then calculate the drop rate and horizon gain that comports to a curve with a radius of 3,963 miles by pulling out our triangles as below. So if I now deconstruct these triangles that we used to get the curvature rate, we can get either a horizon gain or a height loss or drop rate. So recall that within option 1 of the angular resolution, horizon gain is nothing more than the expansion of the lower eyeline resolution angles, or theta expansion. And the height loss or drop is nothing more than the compression of the lower eyeline resolution angles, or the theta compression. So we can then extrapolate these 2 triangles to a greater circle again, and calculate out for a circle what we would have as a height loss or drop, which is again just the theta compression, or the horizon gain using trigonometry, which is again the theta expansion. So for the circle here, with this particular rate to create a circle, you need sine theta is equal to, where theta is that arc angle there between the distance over which you're observing something drop. It's equal to the distance over which you're observing it drop divided by r, the radius of Earth, which yields that angle. And then you're going to solve for the height of that drop, such that the height is going to equal the radius minus the radius times the cosine theta. And you can see from the trigonometry there how you get those angles from those arc lengths and so forth. You can alternatively get a horizon gain or theta expansion formula pretty simply by just using a right triangle. So in this right triangle example, you're going to have r plus a height of u sitting above the surface of the circle. Squared is going to equal r squared plus d squared. You can see just the edges of the right triangle there. And you can then solve for the distance d. The drop h squared is, since it's small, you can just subtract it from r squared from both sides, and then d becomes the square root of 2hr, or distance in miles is equal to 1.22 times the square root of height in feet. So if you just plug in your height in feet above the surface of the circle, you will get the distance d across which you can see. And you can see the exact same formula here on the Wikipedia horizon example, saying that the average person, say about 6 foot, can see about 3 miles, which is, again, just angular resolution. So we can also derive a quick calculation formula any number of ways. We need to determine the exponential rate of loss across a change in distance. So in other words, we need to know what the loss per mile is with each additional mile, or the x loss of feet per mile squared. We can then model this rate of loss two ways. One ignores perspective and models a standard height that experiences an exponential drop rate, or attempts to incorporate perspective and models a standard drop rate across an exponential size change. So here we have our two possible ways to model this, but the same equation. You have a standard drop rate x across an exponential height change, which you could then place into perspective to view something getting smaller with distance and parts of it getting cut off with that distance. So height is equal to x, some constant that we are, it's going to be some unknown standard rate of loss across 1 over the distance squared to give us our exponential height change. And in the other way, we're going to use the same formula, but we're going to be using x here as our unknown exponential rate of loss across a standard height. So again, on the first example, we have an unknown standard rate of loss across an exponential height, and on the second one, we have an unknown exponential rate of loss across a standard height. Both give us the same information. If you need to pause and digest some of these, please do so. Either way, we need to find the drop rate x. So we'll use the standard drop across an exponential size change in order to view this person in perspective. So if we believe the rate of loss is 6 feet for every 3 miles, starting at 0 feet and 0 miles, which are again our two matching points between linear angular resolution loss and our exponential curvature loss, we can then solve for x. So remember, we need to know what the loss per mile is with each additional mile, or x loss of feet per mile squared. So the 6 foot loss at 3 miles becomes a 6 foot loss at 3 squared miles, or a 6 foot per 9 mile squared loss, or 0.666 feet per mile squared. So again, you can change our formula, essentially, or the way of looking at this diagram, to be a just substitute x for what we solve for as 0.666 feet per mile squared, and this person has that part of him essentially removed with that particular distance. So you can see at 1 mile he has chopped off about 8 inches of his legs. At 2 miles he's lost about 2.6 feet of himself, or about half of his body. At 3 miles he's lost 1 full body. His 6 foot has disappeared. At 4 miles he's lost to about 10.6 feet of himself. In other words, if we remove 0.666 feet from the object across the square of the distance, this is what we're doing in order to theta adjust our height in perspective. you can then just take 0.666 feet per mile squared and you convert it to in inches. It becomes 8 inches per mile squared, which is the common formula that people use. Again, this is not terribly accurate. It's only accurate up to about 100 miles, as we'll see, because it works out to a parabola. It's not a circle. We can place this person into a perspective view in an attempt to match our reality, like we talked about, but this often fails to match what we observe because the math was used to fit a false assumption. In other words, keep in mind these formulas are not accurate, but I wanted to show the derivation. Again, the truth of the world is that it is linear. So again, the loss per mile, 0.666 lost below the knees. Then we have 2.6 lost below the waist. Then about 6 foot loss, which is the whole body. And then about 10.6 loss, which is almost 2 bodies. And our inverse square law adjustment here, you're going to be at 1 to 1 at 1 mile, 1 and 4 at 2 miles, 1 over 3 squared at 3 miles, and 1 over 4 squared, 1 over 16 at 4 miles, and so forth. So you can see the conversion there going from right to left, and then you can just place that person within the horizon line and you see what you are going to get chopped off at various distances. So one person here is going to get his legs chopped off at 1 mile. He's going to get half of his body chopped off at 2 miles. We're going to lose an entire person at 3 miles, and we're going to lose 2 entire people, or almost 2 entire people at 4 miles. It's just going to keep going from there. So I just took the picture on the right, and you just chop off a portion of it and you move it into perspective. That's all that's being done. It's an exponential size change with a standard set loss set against our perspective view. And this is somewhat of our theta adjusted parabola, or a parabolic loss. So it can be used to estimate a curve again, but it's only good to a certain point. It works up to about 100 miles, as you can see, and then it just starts to fall away. You cannot make that come back into a circle. So it has a slight overrepresentation of loss, but then greatly underestimates the circle as it goes on. So again, the two curvature formulas are roughly similar to 100 miles, and then they start to break down. Whereas our linear loss, you can see that what we actually lose within our linear world is way up there. So it's much more of a dramatic loss that you have to have in order to live on a curved surface. You have to have these high rates of curvature and loss of an object. So what that means is if you do see an object and you see more of it than you should, it should bring into question that this is a physical phenomenon, that you are losing this object physically behind curve. We already have the quick formula for height gain according to the circle model, and the assumption that we look down across a bulge of Earth to see distant objects, but the distance across a height gain is simply the inverse scenario of the height drop across a distance. So we can invert the drop rate of 0.666 feet per mile squared as the height gain and horizon distance gain. So the parabolic height loss or drop is then just inverted to become the parabolic horizon gain. So our height equal to 0.66 of a drop rate across the mile squared is then inverted. The h becomes 1 over h. So then 1 over h is equal to that same rate. And we can then solve for distance, and it becomes 1.22 times the square root of h, like we derived earlier. And they are, again, very similar in that respect. So the parabolic horizon gain is much more accurate to a circle. But again, the drop formula, when plotted out and compared with the circle, works very well up until 100 miles, and after that, that aspect of the formula breaks down. So before closing, let's look at the Chicago skyline one more time. This time lapse is from a dune at very close to the water, Grand Mere State Park, Stevensville, Michigan, approximately 57 miles away. And again, video link in the description. Keep in mind that the Willis Tower is 1,748 feet high. If you plug it into any earth curve calculator of your choice, you see that the Chicago, all the buildings of Chicago should be hidden behind 2,000 feet worth of curvature, physical curvature. You should not be able to see them. Just like the Skunk Bay footage, the same refraction and miraging effects occur, but again, the image is relatively stable, as if you were just seeing it through wavy water, not that you are bringing this entire object or entire amount of imagery up behind a curve, nor that it is compressing and moving back down again at that rate. It's just not happening. It is not brought up around the curve from downward refraction over water. It just doesn't occur. If the horizon were a physical bulge, we shouldn't see these buildings at all. They should be lost. So recall that the bottom is lost from angular resolution limit, accounting for roughly at this distance about 110 feet at 60 miles. And the remaining roughly 300 feet that seems to be lost is from upward refraction across the warmer surface air over the water. And let's take a look at it now. And you have to ask yourself if this is the Chicago skyline, or you believe that this is this entire thing is a mirage. Again, to me, that's the Chicago skyline. And it's waving and moving slightly up and down, just like the Skunk Bay footage. But just like Skunk Bay, you were looking at those buildings across the water. I am looking at the Chicago skyline across the water. So here's the problem. The explanation for seeing these buildings is that they aren't actually there. So again, they're going to tell you that this is not actually what you're looking at. So he believes that this is some one-time mirage inversion event. But again, there are several time lapses. Then you can see this. Chicago is always visible essentially the same way. It doesn't go down below the curve and then is brought back rapidly upward. It's stable. It's just slightly moving up and down here and there and expanding and compressing here and there. But it's just like all the other phenomenon that we've witnessed with closer objects. So again, the reason is not because of a mirage. The reason that we can see it is because this is the Chicago skyline.
Until I found this photo from Grandmere State Park. This is from Joshua Nowicki, and what you're seeing here is a mirage. We typically would not be able to see this from the Lake Michigan shore. We talked about this last night. Conditions are right on the lake that we're actually seeing a mirage of the Chicago skyline. Very interesting here. Here's what's happening. This is a good example of a superior mirage. So Joshua was on the Lake Michigan shore. He was looking towards the west, and Chicago's beyond the horizon. Should not be able to see it. However, with the right conditions, we have an inversion. We have cold air near the cold lake water and some relatively warmer air above it. This will bend the image of that skyline back towards the viewer. And so typically we would not be able to see this. This image would be viewable from much, much higher in the sky, up in space.
So again, the explanation is that you're seeing Fata Morgana, or multiple stacks of unstable inverted imagery. Again, I want to impart that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction. So again, I'm just showing the Earth curve calculator that must be enacted in order to make these buildings appear. You have at a 6-foot observer height and a 60-mile distance, you must have a hidden height of 2,166 feet, and none of these buildings should be visible. This is not a mirage. That is the Chicago skyline. So again, things get smaller as they move away. Your horizon rises to eye level. That is what is happening. You don't continually shift your eye level downward to see a falling horizon. Again, note all the Earth curve calculators require you to be looking down across a horizon to view another object on the other side of the bulge, going up at another angle. The ground rises to your horizon because we see the world in perspective. It is the top and bottom half of our vision. Your eyes were used to deceive you, and you don't live on a ball. So again, special thanks to everyone who's working hard, taking observations, and trying to put the pieces of the puzzle together. There's many more on here, but I just tried to use the folks in which I've used within the series, at least for parts of the information that they've provided. So in the next video, we will discuss the empirical evidence of deception and biblical significance, and I hope you will watch the end of the series. I think it, again, it's the reason why all of this is happening, what I believe anyway, and I think you'll find it important. So hopefully in this series we discussed angular resolution, and then within the globe model, Aries failure, axial tilt in the human eye vertical field of view as a means to derive Earth's radius, the derivation of the radius by the extrapolation of the angular resolution limit of the human eye, and derivation of the parabolic drop rate within perspective as 8 inches per mile squared. So once again, thank you for watching the series up to this point. I am hopeful and optimistic that eventually we will live in a world that operates on truth and not deception, and that's my continued prayer for the world in which we live. So again, if you can, please watch the final video. It's not very long, and God bless you all.